Introduction to Cloud Computing. Reporters Daryll F. Abion, Joey G. Soriano, Maria Diejhey Martinez. What is cloud computing? It's a distributed computing on internet or delivery of computing services over the internet. Example are Yahoo, Gmail, Hotmail. Instead of running an email program on your computer, you log on in the web email account remotely. The software and the storage for your account doesn't exist on your computer. It's on the services computer cloud. There are three components of cloud computing. First is the client computers. Second is the distributed servers. And third is the data centers. Clients. Clients are the device that end users interact with cloud. There are three types of clients. The mobile, the TIC, and the TIN is the most popular one. A data center. It is a collection of servers where application is placed and it's accessed via in the internet. And the last one is the distributed servers. Often servers are in geographical different places by servers acts as if they are working next to each other. A central server is an administrative server such as monitoring traffic, client demands to ensure that everything runs smoothly. They use a special type of software called middleware. A middleware is also allowed by computers to communicate to each other. Service model. There are three particular service models: the SaaS, the platform as services, and the infrastructure as services. The deployment of cloud services are public cloud, private cloud, community cloud, and the hybrid cloud, or called as the combined cloud. Distributed file system is also merely the fact that physically distributed in terms of setting files, usually within a network or a computer. Allows client to access files on remote hosts as if the clients are actually working on a host. Enables maintaining data consistency, and it acts as a common data store for a distributed application. Simple examples of distributed file system is the Dropbox. The Dropbox keeps your files synced across many computers. This is transparent to operating systems like Windows, Mac, and Linux. It is a transparent distributed file system application. These are the distributed file system requirements. First, it's transparency, it's concurrency, fault tolerance, and scalability. The most attributes inherited by the distributed systems are heterogeneity, consistency, effectivity, location independence, and security.
The network file system. An industry standard by Sun Microsystems for file sharing on local networks that started on 1980s. An open and popular standard with clear and simple interfaces. Supports many of the DFS design requirements. For example, transparency, heterogeneity, efficiency. Limited achievement of concurrency, replication, consistency, and security. Network File Systems, or NFS, an industry standard by Sun Microsystems for file sharing on local network, started on 1980s. An open and popular standard with clear and simple interfaces, supports many of the DFS design requirements, for example, the transparency, heterogeneity, and efficiency. NFS has a limited achievement of the following: the concurrency, replication, consistency, and security. These are the sample of client computer and a server computer using the NFS. And in the middle, we show the NFS protocol shows the relation between the computers, the client computer and the server computer. Client computer Network File System, or the NFS, an industry standard by Sun Microsystems for file sharing on local network since the 1980s. An open and popular standard with clear and simple interfaces. Supports many of the DFS design requirements, such as, or for example, the transparency, heterogeneity, and the efficiency. Also, the NFS, or the Network File System, has a limited achievement of concurrency, replication, consistency, and security. And the following diagram shows the NFS protocol of the client computer and the server computer. NFS trade-offs. NFS volume is managed by a single server. Higher load on the single server. Simplified coherency protocol because of the single server management. Not fault tolerant, scalability is the real issue. Multiple points of failure in large 1000 plus systems. Example of the application bugs, the OS, hardware and power failure, the network connectivity. This includes the network infrastructure. And monitor fault tolerance, auto recovery. It is essential in cloud computing. The Google File System, or the GFS. Google has had issues with existing file systems on their huge distributed systems. They created a new file system that matched with matched well with the MapReduce, also developed by Google. They wanted to have the following: the ability to detect, tolerate, recover from failures automatically. Large files or greater than or equal to 100 MB in each size. Large streaming reads, each read being greater than or equal to 1 MB in size. Large sequential writes that append concurrent appends by multiple clients. Atomicity for appends without synchronization overhead among clients. The architecture of GFS, or the Google File System. Single master to coordinate access, keep metadata, simple centralization management. They fix size chunks to 64 MB. Many chunk servers, 100 to 1000. Files stored as chunks. Each chunk identified by a 64-bit unique ID. Reliability through replication. Each chunk replicated across 3+ chunk servers. Many clients accessing same and different files stored on the same cluster. No data caching. Little benefit due to large datasets, streaming reads. The master and chunk server responsibilities. Chunk servers It is simple. It stores chunks as files. Chunks are 64 MB in size. Chunks on local disk using standard file system. Read-write request specify chunk handle and byte range. Chunks replicated on configurable chunk servers. The design trade-off can have a small number of large files. Less metadata. The GFS master node can handle it. Fewer chunk requests to master node. Best for streaming reads. Large number of small files, one chunk per file. Waste of space. Pressure on master node to index all the files. How about the clients who need the data? GFS clients consult master for metadata, access data from chunk servers, no caching at clients and chunk servers due to frequent case of streaming. A client typically asks for multiple chunk locations in a single request. The master also predictably provide the chunk locations immediately following those requested. Differences in the GFS API or API, not POSIX compliant, cannot mount an HDFS system in Unix directly, no Unix file semantics, an API over your existing file system. API operations, open, close, create and delete, read and write, record append, snapshot. It is quickly created. It quickly creates a copy of the file. Replication in GFS. The data chunks on the chunk servers are replicated, typically 3 times. If a chunk server fails, master notices missing heartbeats. Master decrements count and replicas for all chunks on dead chunk server. Master replicates chunks, missing replicas in background. Higher priority of chunks, missing greatest number of replicas. Consistency in GFS. Changes to namespace are atomic, done by single master server. Master uses logs to define global total order of namespace changing operations. Data changes are more complicated. Consistent. File regions all see as same regardless of replicas they read from. Defined after data mutation. File region is consistent and all clients see that entire mutation. Mutation in GFS. Mutation equals to read or append. Must be done for all replicas. Goal: to minimize master involvement. Less mechanism or least mechanism. Master picks one replica as primary, give it a list for mutations. Primary defines a serial order of mutations. All replicas follow this order. Data flow decoupled from control flow.
Okay, let us proceed with the topic, Hadoop Distributed File System or the HDFS. Okay, so you heard about the GFS and the good things about it, okay? Now, if you're trying to say that you can have it, no, it's not, because GFS is a Google proprietary technology, so it is owned by Google only. Now, the good thing is they publish the technology, though that is the HDFS. Okay? Now, HDFS, what is HDFS? Okay, so HDFS is an open source GFS under Apache. Okay? So when you say open source, it's free. And the design is the same, goes with the GFS. the same architecture, API, and interfaces. So basically, HDFS is similar with the GFS. The only difference is HDFS is free. Okay. Now, how about the HDFS design? As I have said, HDFS is almost the same with the GFS. So the files stored as block. So the transfer of files is by block. Then it is also reliable through replication. Okay, so why replication? Because every time a file is saved, it is saved in 3 nodes, minimum of 3 nodes or 3 servers. It has a single master name, namely the name node. So the purpose of the name node is it is the one who orchestrates or the coordination, the accessing of data, and all the metadata. Okay, so for short, it is the manager. Okay, it is the server, centralized server that manages all the processes. Next, it has no data caching. Why? Because little benefit due to large data sets, swimming reads. And familiar interface. Why? Because yes, it is the same with the GFS, so you should be familiar with its interface, but it is also customizable. Now, how about the architecture? In this picture or this diagram, example here we have a client computer saving a file in a cloud computing. So when you save a file using cloud computing, your file is saved into 3 different servers, namely the name nodes. Okay, we have the name node 1, name node 2, and the name node 3. So 3 is only the minimum. You can have more than 3. Okay. The next architecture I'll show you is that this shows that we have here 2 clients. First client is requesting for read. Okay. But before he reads the data, she first requests a read request to the name node. Okay. So after that, the name node will respond with the data blocks to where the data was saved. Okay. The next client is requesting for the write. He wants to save data to the server using the cloud computing. Okay. Now, here how to talk to HDFS. So HDFS, or how to use HDFS. So basically HDFS is used or was created using different languages like the C, the Fuse, the WebDAV, and other technologies such as HTTP, and many protocols like FTP. Now, in Java, we use the file system and distributed file system classes. Okay, just refer to this chapter 3 of Tom Wright's Hadoop book. Okay, so anatomy of an HDFS file read. So this is the process on how data or a client can read from a cloud computing server. First, a client program requests for data from the name node. Okay, the name node is our master node using the file name. And after that, the name node returns the block location to the data nodes. Then, after that, the client can now access the block individually. So, pwede nang ma-access yung data sa server. So, here's the diagram of that process. So, we have here the client requesting to read the data to the name node. Then the name node respond with the address of those files that the client can now access the files here in our data nodes. And here, it should be anatomy of an HDFS write read, file write, okay, not read, okay. Just addendum, edit this read to write, okay. So how to write to a cloud computing server? First, the client issues a write request to the name node, again to the master. Then the client writes individual blocks to the data nodes, okay, and the data node pipeline the data for replication. So what happens here? The client writes the data on the first data node. Then after the write on the first node, the data node itself replicates the data to the succeeding data node. That's how replication was produced. Then after that, after a block is written, the data node sends an acknowledgement, okay? Acknowledgement of what? Acknowledgement that the data has been written, okay? Acknowledge after the file is written, the client informs the name node. And okay, so this is just the graphical representation of that process. And I think that is the end of our report. So thank you and goodbye.